All right, I think we're ready to begin now. My name's Keith Torrance. I'm going to be the chair for session 4. The topic for this session is land contamination risk assessment and sustainability. So we've got a great program of speakers for this last session, so thanks for hanging around. So our first talk is going to be from Megan Moore, who's from Arup. I will introduce each speaker before they begin, but we have a couple of lightning talks to kick things off from Megan and from Thomas Chen. We're then going to move on to some more regular presentations, beginning with Claire Stone from I2 Analytical, who's going to talk about asbestos dust testing. My colleague Christine Switzer from the University of Strathclyde is then going to talk about beyond the TCLP and the waste acceptance criteria methods. And finally, Helen McMillan from RSK is going to talk about considering climate change and controlled water risk assessment. So very interesting program. So you've probably seen this slide from some of the presentations yesterday. It just shows the UN Sustainable Development Goals. And as you probably know, there's 17 goals. The ones that probably relate most to contaminated land are goal number 8, which is decent work and economic growth. Industry, innovation and infrastructure, goal 11 for sustainable cities and communities, climate action, which is goal 13, and finally life on land, which is goal 15. And I think each of our talks will really touch on some of these goals and how they can be achieved through redeveloping contaminated land. I had the opportunity a couple of weeks ago to visit a site in Glasgow. It's the old Gravings dry docks in Govan, which hopefully some of you have had the chance to visit. I think it's a fabulous site if you have any interest in industrial archaeology or the history of the Clyde. It's a great place to visit. Sadly, it's been abandoned now since the mid-80s and basically fenced off and allowed to kind of decay, as you can see in this photo here. So quite a contrast from, the vibrant days when these dry docks were used to repair and do maintenance on ships in the dry docks there. It's a great illustration for our theme because, this is a parcel of great real estate in the centre of Glasgow. It's right on the river. It has tremendous potential to be used, beneficially for the community, and yet it's essentially been fenced off and off limits really to the people of Govan. And, I wonder whether that would happen if it was a site in, say, the centre of London or one of the more wealthier suburbs. So great piece of property, but a bit of a tragedy that the people of Govan really can't make good use of this site. So I think it illustrates, part of the theme of our talk, where the whole sustainability aspect of contaminated land remediation is to take land that's essentially waste and out of service and return it to a beneficial use for the whole community, not maybe just as probably would have happened to this site being developed for upmarket expensive of housing. But if you ever get the chance, it's well worth a visit, and some great historical archaeology there. So before we kind of kick off, I just want to remind everyone, to tweet and use the hashtags to promote the conference to your colleagues and any of your contacts on Twitter or LinkedIn, and we very much rely on those social media now for getting news out about what SCLF is all about, and for promoting events such as this. Great, so without much further ado, I'll introduce our first speaker. Megan Moore is a senior environmental consultant who's based in Arup's Belfast office. She's got more than 7 years of experience in that field, with a particular focus on environmental impact assessments. She has an extensive experience in environmental management on construction sites, and has also been involved in a number of construction schemes producing construction environmental management plans and leading the environmental design and review. So with that introduction, Megan, I'll open the floor to you.
Thank you very much, Keith. Hopefully you can all see my screen now. So good afternoon. As Keith said, my name is Megan Moore and I am a senior environmental consultant at Arup. So I just want to welcome you to this really high level overview presentation on the UN Sustainable Development Goals and me. And we will be taking a quick look at why the SDGs are important and why we as professionals working in the built environment should aim to incorporate these into our design and projects. So the agenda will be having a quick snapshot look into 4 key questions during this short presentation. So 1, why are the UN Sustainable Development Goals? Why are they important? What does this mean for Scotland? And how can we respond in the built environment sector? So what are the UN SDGs? So there's 17 goals to transform our world. They are a call for action by all countries, poor, rich and middle income, to promote prosperity while protecting the planet. They recognise that ending poverty must go hand in hand with strategies that build economic growth and address a range of social needs, including education, health, social protection and job opportunities, whilst tackling climate change and environmental protection. And within these 17 SDGs, there are 169 targets, and each goal typically has between 8 to 12 targets. These 17 UN SDGs are a global response to the current interconnected global challenges. The 17 goals and 169 targets provide a shared vision of what a better world will look like. So how should we be engaging with the SDGs, whether this is in work, university, or in our personal life? And what can we actually influence? And these are questions we should be asking ourselves as part of our working and personal life. So why are the UN SDGs important? Change is needed. We're at a defining moment in time. To limit our rising temperatures to an increase of 1.5 degrees Celsius will require rapid, far-reaching and unprecedented change in all aspects of society. Global net human-caused emissions of carbon dioxide would need to fall by 45% from 2010 levels by 2030, reaching net zero at around 2050. This means any remaining emissions would need to be balanced by removing CO2 from the air. The UN reported up to 1 million plant and animal species face extinction, many within decades because of human activities. And Sir David Attenborough has also warned world leaders over the extinction crisis and its effects. Hunting, habitat destruction and other human activities are pushing a rich array of animals to the edge of oblivion. Human encroachment on the habitats of wild animals also increases the risk of outbreaks of new diseases. However, the world can reverse this biodiversity crisis, but doing so will require proactive environmental policies, the sustainable production of food and other resources, and efforts to reduce greenhouse gases. Now, governments are responding. So in 2015, the UK government committed to achieving the UN SDGs. And these goals aim to improve peace, prosperity, access to healthcare and education, whilst also tackling climate change worldwide. The SDGs were also known as the Global Goals, and these replaced the 2001 Millennium Development Goals, which were only covered by developing countries. The new goals apply to advanced economies like the UK. Each country signed up to a deadline of 2030 to achieve the SDGs and has to report on how they're performing. So I did take a look on the interactive map before I came on, and at the moment the UK has reached 79.97% of achieving the SDGs, and they currently sit 17th out of 165 countries that are scored. So they've dropped a bit from last year. They were 13th whenever I did last check, so they have dropped. The UK has dropped a bit, but they still are on target of reaching these. However, there is a bit of work that needs to be done. So what does this mean for Scotland? World leaders will gather in Glasgow in 2 months' time for the COP26 Climate Change Summit. The Scottish Government says its targets to reduce emissions are some of the toughest in the world. The Scottish ministers want renewable energy generation to account for 50% of energy demand across electricity, heat and transport by 2030. And onshore wind delivers about 70% of the capacity, followed by hydro and offshore wind as Scotland's main sources of renewable power. So the Scottish Government has set a legally binding target to cut greenhouse gas emissions to net zero by 2045. This is 5 years ahead of the date set as the UK as a whole. And net zero means any emissions will be balanced out by schemes to offset an equivalent amount of greenhouse gases from the atmosphere, such as planting of trees or using technology to capture carbon and store it. Trees are the most effective way of absorbing CO2 from the atmosphere. And to meet these targets, the UK needs to have a net increase of 32,000 hectares of woodland planted every year for the next 30 years, equating to about 1.5 billion trees. Figures show that most of the trees planted in the UK were planted in Scotland. 11,000 of the 13,700 hectares that were planted in 2019 to 20 were planted in Scotland. So by 2024, the Scottish Government aims to be creating 18,000 hectares of new woodland per year, with the ultimate goal of having 21% of Scotland's land covered by forest, compared to the 19% that's covered today. Scotland have published their climate change plan update in December last year, which reflects the increased ambition of the new targets set in the Climate Change Emissions Reductions Target Scotland Act of 2019. This update to Scotland's 2018 to 2032 climate change plan sets out the Scottish Government's pathway to their new and ambitious targets set out by the Climate Change Act of 2019. It is a key strategic document on their green recovery from COVID-19. So how can we respond in the built environment sector? A sustainable future involves transformative change in every aspect of society globally. This requires more than incremental improvements or piecemeal approaches. In all activities, the SDG challenge us to expand our perspectives. In the built environment, our role should not just be as the best producer of outputs we're contracted to do, but also the enabler of broader outcomes we and our clients should be striving to achieve. Our focus should be to develop designs and services that can produce safe, more inclusive, resilient and sustainable cities and infrastructure. One of the key differentiators will be our integrated total value approach, completed with strength in system thinking, network modelling and regenerative design, among others. New design paradigms are emerging based on human-centred principles and system-based approaches. Good design will increasingly mean better lifecycle performances, and existing assets will be repurposed, reassembled or retrofitted rather than being replaced. We need to go beyond the lean, clean, green design to regenerative design that values natural capita. We need to produce adaptive and regenerative designs, ones that make a sustainable use of natural resources. So just the diagram on screen shows us that we need to go beyond our conventional design if we want to prevent ecological loss. Even best practice of today, the green design, is not enough. We need to go beyond sustainable to restorative and then to regenerative designs if we want to ensure that ecological gain in our designs. And we need to be working collaboratively, both engineers, planners, ecologists, landscapers. We all need to be involved in the beginning of our designs. to think about what SDGs we can include to better our project, rather than looking back and saying our project then incorporates this and this. So thank you very much for your time.
Thank you, Megan. That was very informative. I think we do have some time for questions. I do see one question in the box, which I'll just take a look at. Oh, right. I don't think it's actually a question. So I guess I have a question then, and that's really, you know, have we kind of picked the low-hanging fruits as far as meeting our targets? Because it just seems to me that it's going to get increasingly more difficult to, you know, address things such as heating, for example, and meet those goals.
Definitely. As I say, whenever we were looking at the SDGs, the interactive map, now you can go onto the SDG website and go on that and click and see each country. You know, the UK has dropped. It's dropped from late last year from 13 to 17. There's absolutely a lot more that could be being done. There's targets that we're not on track to achieve. But that's the government really needs to step up. But I suppose as an EIA coordinator, I'm definitely the past couple of years definitely noticing developers now having more of an interest in sustainability and starting to mention the word SDGs. And I do think in the next couple of years, the panic will set in that more will have to be done on developments to essentially not just make them more sustainable, and not just to have that as a tick the box exercise, to really have an all singing, all dancing regenerative project.
Great. All right. Thanks again, Megan. And I think there are a couple of questions in the answer box. If you are able to maybe answer those, or I think somebody looking for information, some web links, if you could take a look at that.
Yes, yes,
Before
I'll
the
put
end
that
of
in
the
now.
session. That
I'll
would
go
be
in,
great.
yeah. No worries.
Great. Okay, so our next speaker was supposed to be Thomas Chen. I know he's based in the United States, so there might be some time zone issues there. So I think we should move on to our next speaker, who is Claire Stone. Can she be made a presenter? Anyway, Dr. Claire Stone is the Group Quality Director for I2 Analytical and I2 Fast Limited. She has a PhD in analytical chemistry with specific expertise in inorganic analysis in the biomedical, oil and environmental industries. She uses her knowledge of these fields to bring scientific and technical support to customers and trained staff at I2 laboratories. Claire has worked for I2 Analytical in a variety of technical roles prior to being appointed quality manager, and has been instrumental in the development of specialist testing methods offered by the laboratory. And she's going to talk in one of these methods, asbestos dustiness testing. Claire?
Wonderful, thank you very much. Trusting that you can all see my slides. So thank you for allowing me to talk. I have spoken at a Contaminated Land Forum event in the past, it was some years ago, and I know about 4 years ago, one of my colleagues actually talked about the same area of testing, but things have changed a bit, and I think it's quite relevant to land remediation and reuse, and how to make the most of the big bad beastie that is asbestos and what can be done with it in soil. So without further ado, I will move my slides along. So today I'm going to give a bit of a brief background on asbestos, what it is, where is it, what do we do with it, why is it useful. I'm going to go through some traditional methods for analysis of asbestos in soil. This is largely sort of just to give everything a bit of context if perhaps this isn't a familiar area to you. and also lays really good groundwork for discussing the asbestos dustiness test and the relative benefits that it can bring to perhaps somewhat tricky sites, particularly where you're looking to reuse a site that perhaps might otherwise be deemed as a high risk. So what, where and why? So asbestos comes in 6 major forms. You've got the fibrous asbestos, which is chrysotile, white asbestos. And then you've got the amphiboles, which are chrysidolite, amazite, actinolite, amphophilite, and tremolite. Chrysotile is it's called serpentine. It's fibres that are basically wibbly wobbly. They look a bit like a snake. Whereas the amphiboles are all long, thin, needle-like structures. So understandably, the 2 different types of fibres present a slightly different risk when you're looking at the inhalation pathway. Asbestos, that's how it affects people. So where do we find it? Well, it is natural. It is a mineral. It's mined. And the earliest use is somewhere around 4,500 years ago. So it's been used for a long time, particularly for strengthening earthenware back then. More recently, we've used it for sound absorption, tensile strength, resistance to fire, heat, electrical and chemical damage. We're all familiar with asbestos lagging, but obviously also textures, coatings in houses, all sorts of different uses. And it does still kill quite a few people each year. This is because of the long residence time once you have inhaled asbestos fibres for them to potentially cause an issue. And ultimately, what, where and why are we looking at in soil? Well, quite a lot of that through demolition, through reuse, through even just burying it in the soil, can actually reach the soil environment, and then that potentially can cause some issues. So what it looks like and where to find it. Well, these are some slides that a former colleague of mine called Asbestos in the Wild. So these are asbestos, you've got some cement, you've got some roofing, you've got lagging. But for a laboratory, what we normally end up finding is the stuff in the bottom right-hand corner, which is largely unattributable to its original form. There are reference documents about what it looks like and where to find it, and sort of various contexts, various uses, etc. And that's in HSG 264, the survey guide, and there's also HSG 248, which gives a general protocol on asbestos sampling and bulk analysis. And it has recently been updated to include a soil-specific section and a soil-specific optional analysis route in the Appendix 7. But I'm not going to talk too much about that today. So what does the lab do when they get a sample? They say, oh, I've got asbestos on my site. I think I want to have it looked at, I want to have it confirmed. What do we do? First of all, we'll normally inspect the entire sample visually just for any large pieces of ACM, because then that would actually be a bulk material that's been submitted to the lab. What we then do is we take a representative subsample, somewhere around 100, 200 grams, depending on the laboratory you're using. And then we take that subsample, we dry it, and then we look at that underneath a stereo microscope to look for smaller pieces of ACM, small fibre bundles, things that you wouldn't normally be able to see with the naked eye. So that is kind of the preliminary stage before we then do what is commonly called stage 1, which is the soil screening and identification stage. This bit must be accredited by UCAS. There are guidance notes in the form of UCAS document lab 30 and HSG 248 on exactly how we do this. We do it on a subsample that is dried because it is much easier to look at the sample, pull it apart, interrogate it, to be able to find those fibres, find the small fibre bundles, find the pieces of ACM, much easier in a dry sample. It's looked at by eye and under the stereo microscope, because sometimes things look a little bit different when you're looking underneath the microscope. We remove any suspect materials, fibres, fibre bundles for identification, and then we identify them by polarising light microscopy. Now, luckily, one of my colleagues has provided us with a video so you can see how we actually do an identification. So this is a video of how you identify chrysotile. You mount it in a particular refractive index liquid, and it shows characteristic properties. So this is being rotated through a plane of polarised light, and it's showing what's called extinction. So the fibres appear and disappear as they get rotated through the plane of polarised light. That is very characteristic of this form of asbestos with this refractive index liquid. We look at it a slightly different way. We can look for the sign of elongation, which is how asbestos sort of grows and shrinks. Don't just think about it getting longer, it gets broader as well. This sort of is another positive indication of this particular type of asbestos. Natural fibres won't do it. other types of asbestos fibres won't respond the same in this refractive index liquid. If we don't apply any filters, that's what it looks like, which isn't the easiest thing to look at and go, oh yes, I've got some asbestos there. What we're ultimately looking for is this thing called dispersion staining, which is where when we rotate the fibre through a plane of polarising light, they change colour. They go between the bluey colour, bluey purple, through to reddish colours. So it's quite obvious. So quite often we get asked, oh, are you sure, definitely sure it's asbestos? Yes, because of the way that it is behaving. And it is very difficult to get a false positive. If the asbestos has been sort of abused, you can end up with other complications, but there are other signs that we look for as well. Stage 2, gravimetric quantification is also known as hand picking and weighing. There are guidance documents out there. Typically, the reporting limit is around 0.001%, but that does relate to the sample mass that you take for analysis and balance sensitivity. And what we do is we remove anything that we find and we weigh it. And if it is the bulk material, we use the percentage content from HSG 264 to say, oh, that's a lump of cement, that's X% asbestos based on the type that it is. So actually, that's fine, we know what that is, and we go through and we quantify it that way. The fine fraction is examined by stereomicroscopy, and all of those fibres, fibre bundles, PCMs are removed and weighed. That gives us our total overall asbestos content using the stage 2 quantification method. To give you a bit of context, these are actually some validation samples. So on the left, we've got chrysotile at 0.1%, large visible fibre bundle. These little bottles, for context, are the same size as these small water bottles that quite often you take for volatile sampling. They're just clear ones. 0.01% is still visible, 0.005% still visible, and 0.001%, I have circled it to make it a bit easier, but you can actually see it by the naked eye. Obviously, you're not always going to find asbestos nicely clumped together like that. Quite often it will be spread out, but it is actually visible to the naked eye at that concentration, something which people often sort of miss because it's, it's microscopic, isn't it? So what do we do with stage 3? Stage 3 can be done as a combination on top of stage 2, or it could be done where we can't hand pick and weigh, but the sample is positive for asbestos. The soil sample is mixed with water and it is filtered. And on the filter, that's where the asbestos fibres sit as we go through and filter it. And then we go off and we look at that filter underneath a special type of microscope called a PCOM, phase contrast optical microscope. That gives us a slightly different picture. It looks like that thing in green. But what that gives us is information about the length and width of the fibres from known density values. That means we can calculate, we've got the volume, we can calculate from the density, we can calculate the equivalent mass. This is all important when it comes to the dustiness testing, because this is the fundamental part of what we then do. So fibre counting and measuring data, we get a lot of data for each sample that we test. So this is a real sample example data. So we've got the measurements we've taken in blue. So we've got the fibre length, fibre width, and the calculated fibre volume for 2 different fibres that we've counted and identified under the PCOM. We know how much sample we've taken. We know how much soil. We know the ratios that we've used. And we know the density. Therefore, we can calculate the equivalent mass asbestos concentration. So for these 2 fibres, they've got the equivalent concentration of 0.00081%. From this data, we can also look at defining whether these fibres are respirable or not. And from that, you can also calculate a respirable fibre index, which gives you an indication of the fibres you've got, how many of them are respirable, what's the potential for release that way. But it's kind of a mathematical just calculation from data that exists. So this is where we start thinking about the context of use of this data. Should we do, if we find some asbestos and we need to know how much is there, do we need to know, is it stage 2 or is it stage 2 and stage 3? And it all comes down to what you're looking to do with the data. Is it a highly contaminated site where you're looking for a waste disposal route and you need to know at a high level, is this bigger than 0.1% or is it lower than that? Or are you looking at something from sort of a human health risk assessment point of view? Perhaps you're looking at, oh, actually, can I reuse this material? Can I put it here? Can I put it there? And then you probably do want the information about whether there are free fibres and respirable fibres present. But these will all just give you numbers that you then need to do some kind of modelling with to work out whether these are likely to be an issue or not, or indeed look them up against an SGV that doesn't exist yet. Many of you will have probably heard of the Blue Book for Asbestos Analysis. It's been cross-referenced in many places. It came, it went, it is now withdrawn. It was a step through of the soil analysis method. It was written by a large group of laboratories, and UCAS were involved as well, and some people on the consultancy side to actually make sure the data that was generated was of use. There were some contentious elements, but these were largely dealt with, and then the final document was issued. There were some requirements in there around detailed reporting, so you get a lot of information about the fibres that you've got, the length of fibres, the dimensions of the fibres, if you've got different asbestos types, how much of each one. But at the moment, there is no desire to publish it through the Standing Committee of Analysts, so an alternative route is being looked at such that this method can then come out and be a good viable method. Because I mentioned before, there is a reference document in HSG 248 that is largely around site surveying. It's a very different analytical protocol, gives you very, very different data. So we're trying to get this method published, so actually there is more of an industry standard reference method. Where does the data go to be used? It goes into a variety of different types of modelling. We've got the Joint Industry Working Group decision tool, which can be used for either working out whether something's licensed, non-licensed, etc. That looks for further detail from the laboratory. It asks for the degree of degradation of the fibres that we've received, clarification on the type, whether they are clearly identifiable or that is a piece of cement, or whether it is a piece of probably cement debris. And that is quite different because that helps you work out whether it's licensed or non-licensed. Quite often where queries are asked around this, we find that a picture paints 1,000 words, and just sending through an image of the fibres and what they look like is enough to sort of provide some reassurance. And a detailed quantification breakdown is often required to input into that tool. Additionally, the Society of Brownfield Risk Assessors have also developed a white paper. This discusses airborne asbestos fibres. There's no guideline value proposed, and really it just raises lots more questions of actually should labs be looking at much lower concentration levels, which are possible, but with totally alternative techniques, looking at electron microscopy. But something that they were trying to do was standardise lab volumes for testing, which I think is very useful. We appreciate that on site, sometimes it's very easy to take a large sample, sometimes it's not. You need to take lots of small samples, maybe you can only get one. But the important thing is how representative is the material that we look at underneath the microscope compared to the material that we've received. And there's a lot of discussion. So there's some interesting things by SOBRA out there if you want to have a look, if you haven't already. So those are what currently exist in sort of routine risk assessment, asbestos quantifications in soils and the different tools that you can put it into. But that just gives you a number, or it might give you a few numbers for different types of material and quantities in your soil, but it's only part of the picture. It doesn't necessarily help us understand the risk. Yes, we can look at whether it's chrysotile or whether it's amphibole, but that's kind of it. So what else can we do? What can we do to help work out what represents a risk? And that really is where the dustiness method comes in. So first of all, we need to understand the risky bits of asbestos, and they are the respirable fibres. They're those that will penetrate beyond the terminal bronchioles into the gas exchange region of the lungs, and they're the ones that represent significant risk to human health. They're clearly defined as being less than 3 microns in diameter and greater than 5 microns in length, with a specific length to width aspect ratio, which is greater than 3. It's important to think that it's not a dust. The asbestos itself is a long, thin aerodynamic fibre. And as I said, chrysotile, wibbly wobbly, amphiboles nice and straight. Amphiboles do present a greater risk. So what do we know? Well, from a paper published by Addison et al., which is heavily referenced in many asbestos guidance documents, they did a piece of work where they took some dry soils containing 0.001% asbestos and found that that could release fibres greater than the current control limit. But that was a dry soil. what they also found is if the soil is wet, there is significantly less chance of the fibres becoming airborne, and that's why it's a traditional suppression technique when working on site. They did this under laboratory conditions, not necessarily representing anything to do with how much people breathe in or how much wind there was. This was their controlled experiment. Okay, so we know that it's a problem. We know that there's only one way to, you know, we've got some reference methods that's going to give us, we know that particular Addison number of 0.001%, and that could be involved, sort of revolved back to soil concentrations. But what we don't have is real sort of live sampling data so much. Now in America, they do like their activity-based sampling. The US EPA are very fond of this. This involves people riding around on bikes, doing gardening or whatever, dressed in RPE and taking air samples while they're there with the pump on their back. That can then be measured at the laboratory, get an indication of fibre release and how big the issue is. In the US, they love that. The UK, pop-up tents are more favourable. You can look at standard air monitoring, but that's all retrospective and it's highly visible. You can also calculate things theoretically, which is what I said. But what we do is lab testing. The method principle is a soil or bulk sample is rotated in a metal drum, constant air is passed through the equipment, and the dust generated is collected along with respirable fibres on a filter. So ultimately, we know how much dust is generated, and we also know the asbestos fibres that are generated. And we've already said we can measure those and work out whether they're respirable or not and what type they are. Get a wide range of output data, dust, and also a breakdown of the types of fibres. The test is run in triplicate, so you get some robust data at the end. But the bit where it's really interesting, and this is just a sort of quote from one of our customers saying they've used it for lots of different reasons, it is more of a tool, it's not a method. We can fiddle with the sample, we can modify moisture, we can add more, we can suppress it, we can look at how much moisture you need to suppress something if you're working on site. If you're looking at remediating a tricky site, we can look at what binding agents can be added into the soil to stop the asbestos being released. So perhaps something that was presenting a problem, perhaps is less of a problem if we can immobilize that material. We can look at optimum concentrations, look at all of that, and you can do that modeled off site, so you're not having to fiddle about on site and perhaps raise something potentially contentious in the area. We can also do other things like manipulate the sample, look at the fine fractions, look at bulk materials, pre-treat something. I've had whole cores submitted for analysis. There are all sorts of different things we can do. We can model different soil types. We can model different weather. We've even had that as a request. You know, my site's in Wales and it's very wet. Can you come and have a look and see what the moisture content does? But ultimately, with this technique, it's about what you want to know as a contaminated land industry, what data is useful to you. And we think that this method is quite a useful thing in terms of looking at that and sort of adding extra value onto just a numerical value. And that brings me to the end. Thank you very much.
Great, thank you, Claire, for that. That was a very topical presentation. What I'd like to do is maybe keep all the questions to the end, and we'll bring back all the panelists except Megan, of course, if that's fine.
Yeah, absolutely.
Great. So moving on, our next speaker is Christine Switzer from the University of Strathclyde. Perhaps you could make Christina a presenter. Great. So Christine's, as I said, is a lecturer in the Department of Civil and Environmental Engineering. Broadly, her research interests lie in the fields and areas of contaminant fate, transport and remediation, as well as rehabilitation of post-remediation soils. She is a co-inventor of the patented smouldering remediation process that has been deployed successfully at contaminated sites all over the world. She and her co-inventors were presented with the Lord Ezra Award for Innovation in Combustion Engineering in 2009, and the commercial team was awarded the American Academy of Environmental Engineers and Scientists Superior Achievement Award in 2017. So Christine, over to you.
Okay, thank you very much, Keith. Okay, I think everything's working. Thank you very much for the introduction. I would like to acknowledge my co-authors, PhD students, Precious Chisala and Andrew Robson, here with me at the University of Strathclyde, and my collaborators at Vanderbilt University, Roseanne Delap and David Cosson. I would also like to introduce my potential co-presenters. I was very grateful to see that dogs are welcome as part of the conference welcome pack. Luna and Foxy might join us. At the moment, they're both sleeping, but that could change in any moment. I don't think I'll apologize for that because it might be a nice break for everybody. Briefly give you an outline of what's coming. I'll give you a broad introduction to who I am and what I do. And then I'm going to introduce the LEAF methods, leaching environmental assessment framework, and place it into context alongside other testing methodologies. And then I'll walk you through a couple of case studies where we've applied the LEAF framework and learned a lot about these particular sites. Okay, my background is in remediation of organic contaminants, and that's actually where I started this journey into learning about metals and how they behave in the subsurface. Smoldering remediation has been my baby since around about 2005. It's the reason I moved to the UK in the first place, was to develop this process. We take contaminated soils that have high concentrations of heavy organic liquids in them. We can ignite them locally and through smoldering combustion then destroy those contaminants in place, leaving behind clean soil. So you can see the before and after here. And with these soils after remediation, if we start looking at them under the microscope, they are a bit different than if they had never been contaminated and never been remediated. The temperatures that we see for smoldering can range from 500 degrees up to 1,000 or more degrees Celsius. It's a short duration exposure, but it's enough to transform quartz from alpha quartz to things like tridymite and cristobalite, which tend to be flatter structures of quartz. We also oxidize iron, which is why in the picture it's quite red, because it's an iron-rich sand that was used for that particular test. And with those temperatures, if we know we're changing the grain, then if there are other contaminants that are present, and for something like coal tar or heavy oils, there's often a load of potentially toxic elements that are there already with the organic liquid, or they might be present from other activities in the soil. If that soil is hot enough that we're transforming quartz, what could happen to these other elements that are present as we're changing the minerals, as we're changing the subsurface conditions, as we're heating? There's a lot going on to understand. So that was my starting point for this work. But I'm not going to talk about combustion today. I'm going to talk about testing. The Leaching Environmental Assessment Framework is something that has been under development for, I'd like to say, decades. When I started my PhD, I was actually working in the research group that was working with the US EPA to improve the methods, and they were added to the SW 846 compendium in 2012, which makes them, from an EPA point of view, very young as testing methods. Typically for leaching assessment, the standard approach in the US was to use TCLP, toxicity characteristic leaching protocol, which is somewhat analogous to the waste acceptance criteria test here. It's a single point test that looks at how much of a substance becomes available at those conditions. And the challenge is that it provides often quite limited information. In between the single point tests and the methods that I'll be describing in more detail, we have sequential extraction methods, where by varying the solvent that's used, You can make predictions about whether something is going to be readily available, whether it's sorbed and will become available over time, or whether it's quite strongly bound into your material. Some of the challenges with sequential extractions are that they can be inconsistent depending on your soil characteristics. The mechanisms are attributed to the solvent. There's quite a lot of research in it, but you often need to vary the method to suit your material. And if you get something wrong in the method, because you're doing sequential extractions, then overestimating in one pool of material leads to potentially underestimating in another, which can be both leading to like over-prediction problems or under-prediction problems depending on your circumstances. The leaf tests are take a somewhat different approach to both of the methods that I've described already. There are 4 tests. There are 3 different kinds of tests, and then one is a different way of doing the same test. 1313 is pH dependent leach availability, so you're looking at pH range between 2 and 13 and what happens across that whole range. Column leaching is what it sounds like. You're passing fluid through column and measuring what comes out from it. The monolith test is somewhat different from these others because instead of looking at granular materials, you're looking at a solid, or it could be a compacted soil made into a monolith. So it's looking at it in a different potential release scenario. And then the last method, 1316, is a substitute for 1314. If you don't have columns, then you could do it in a batch method instead. These are all integrated through data management and modeling tools, so you can look at other conditions as well, not just what you measure, but based on the information that you know about your material, then you can look at conditions you can't necessarily reproduce in a lab, like reducing conditions. That's quite difficult to replicate in a lab because of the controls. The downsides to leaf are that you require a fairly large amount of material, so between 500 grams and a kilogram to work through the tests that you might need to do, and it's also quite labor intensive. So I'm going to focus on 1313, 1314, and a bit of the data management and interpretation of it. This is 1313 in a bit more detail. I mentioned before pH between 2 and 13, and you can see the sample points, the test points between 1 and 9 that span those conditions. Importantly, you usually have between 4 and 5 that are spanning conditions that you would normally see in the environment. So pH 4 to 9 is pretty well represented. These require 20 gram samples, or you can get away with 10 grams if you're limited in material and it's reasonably homogeneous, but there are errors that come through when you go with a smaller specimen. You have 9 target pH values in order to represent the full curve, and these have a tolerance of plus or minus 0.5. Some of them are very easy to get. The T1 and T9 are usually very easy. The stuff in the middle, because it's essentially a titration curve, it can require a bit of iteration, which is why you need a reasonable stockpile of material to be working with. Method 1314, column leaching, you're pushing water through the column and you're measuring what comes out in native pH conditions. It's a fully saturated system, and flow rate is, it can be adjusted a little bit, and the benefit to that is it means that you're not in the lab at 3 in the morning collecting a sample. You can slow it down to a certain tolerance and let it go until a more civilized hour to collect your sample. But the range is there to make sure that you're never running too slow or too fast. Like the previous method, there are 9 points, but what they are instead are collection points where you swap over the container. So you're always collecting leachate, and then you're tracking the release of substance into that leachate over time. Just to show you the alternative method for column leaching, if you don't have the equipment or the material, you can always do it as a batch test instead. Samples of 20 grams. Here you don't have to iterate like 1313 because you're not trying to target a pH, you're targeting different liquid to solid ratios. So it's very easy to control that. Okay, moving on to my case studies. So where I started with this was remediated soil. And not sure if you can see my cursor on this, so but I hope you can. Okay, the remediated soil, we were looking at what happens to the potentially toxic elements within that soil before and after remediation, so with an organic contaminant in, and also if we spike a number of elements in before we remediate it. So the elements that we added, cadmium, zinc, lead, copper, nickel, and mercury, we were then able to track through that and see what happens with it. Just to give you a bit of an orientation, I'm going to focus on one element where there's a very clear difference that's happening. So this is the method 1313 data, where you have pH along the bottom and then available content, so what's coming out into solution. And you can see a bit of variability, change in arsenic concentration across the pH range, but there's a really interesting difference when we start to look at remediation. So the blue diamonds are our before sample. This is our soil without contamination. And then the after, where we've contaminated with coal tar and then remediated, is the red square. So we have a shift between them where the available content is increased a little bit. This is arsenic, we didn't add any. It's a very trace level of contamination that's present in the soil. I think it's below what would be considered as just naturally occurring there, but we are making it slightly more available because by smoldering, by combusting the organic contaminant that was there, we destroyed the natural organic matter where that arsenic was partitioning. So that's one visual difference that's apparent. And then we can look at how that affects arsenic release over time. So the same color codes are there. The blue indicates the soil as received, and then the red is after smoldering. So you notice that even though we've changed the availability somewhat, the release is quite slow in comparison to the starting material. When we added the cocktail, we actually made everything more available, which is why it's slightly higher in this graph. But then after remediation, we have destroyed that. So by making it more available and then burning it, we've probably released some of it into the emissions. So there's less to release into the soil. Moving on now, so there's a lot more stories. There's a very rich data set here that I don't have time to do justice to. I just wanted to walk you through a few highlights so that the same symbols are consistent here, where we have not a lot of cadmium in the soil until we add it, and then it is relatively available, increasing as pH decreases. How that plays out in terms of release into our surroundings, because of the native conditions, we're actually in a very low amount that's present and a very low availability, so that's quite slow release of the native material. After remediation, because we've destroyed the organic matter, because we've also shifted the pH somewhat, we've made it more available. But these are tiny concentrations that are coming out. Relative to everything else, the cadmium that we spiked in stayed available. That's not surprising. Once we contaminated that with coal tar and smoldered it, we have actually reduced the amount that's available, but it comes out of solution pretty quickly. So we have stabilized some of that cadmium. Lead follows a similar pattern to cadmium, and where there's not a lot in the background. It increases in availability as pH decreases, and then we add some and it stays relatively available. And that has played out in terms of the releases. The last one I wanted to highlight is phosphorus, because mostly I've been talking about contaminants, but phosphorus is a real benefit in this case. What we noticed, and it wasn't so apparent with the 1313 data, because pH changes are more complicated. But when we look at the leaching and we look at what grows in the soil, we have changed our phosphorus from something that is very it's very soluble, so it releases into solution pretty quickly, and then disappears. So there's not a lot there to support life. But after we've remediated it, we have transformed that phosphorus into something that is a slower release over time. So you notice the difference between the blue and the red, and it's releasing slower over time, and we're actually releasing more. So we have transformed our phosphorus into something that is more regulated in the soil and therefore more able to support life. And that's one of the real benefits of this method, is that you don't always have to look at contaminants. You can look at other elements and elements of interest, elements of value. The key thing to take away from all of these interpretations are whether you're dealing with availability limited conditions or solubility limited conditions. Availability limited means that it's not going to change as your conditions change. You're limited by mass transfer, what's going to come out into your surrounding material. Where solubility, it's very much tied to pH and other conditions. If you change your conditions a little bit, you could increase your release. Phosphorus is a very good example of solubility limited release, where it is very much dependent on the solubility in the native conditions that you have, and that here is a benefit. Moving on to my second case study is very different. We're looking at copper mine tailings, but the same approach applies here. So Copperbelt province is in the north of Zambia, or actually in its center if you look at it geographically. Zooming in to Copperbelt province, you can see how blue, this is just taken from Google Maps. It gives you an idea of the extent of copper exploration in the region. It's very rich ore. The percentages of copper are up to something like 50,000 milligram per kilogram. It's very rich compared to some of the other copper deposits. The sites that we looked at were in two different towns, Kitwe and Luanshya, that both pretty much developed around copper exploration. So you can see from the map in the top left that the tailings dam, the disposal site for the copper waste, is pretty much surrounded by housing and businesses in Kitwe. And the image on the right gives you an idea of what the tailings look like in practice. They don't grow very much. There's very scrub vegetation, if any. They're very rich in copper because of limitations in mining technologies at the time. So there is a significant amount of copper and a reasonable amount in cobalt in some of them as well, that we're looking at it from the point of view of not just remediation, but also resource recovery. There is more copper to be taken from these waste materials, well, which we can hopefully do alongside stabilizing them and making them safe. There's a lot going on here, but I'm not going to spend time going through everything. Copper is on the left-hand side, that's method 1313, and it's the second frame down, where you can see that below around about a pH of 6, copper becomes very available in all of our tailings and their bottom soils, and that translates to the leaching profiles that you see on the right-hand side, copper being in similar position here, where it's released pretty readily from all of the tailings. There's not a lot else in terms of contaminants in these materials, so it really is a good candidate for resource recovery. And that's what we're trying to understand now, is going back to mineralogy. aging, how much those affect what's there and what we can do about them. And my last case study is completely different. We're not looking at remediation, we're looking at extraction from wastewater treatment biosolids. So how can we recover more of that phosphorus that's present? Typically, land application is an output from wastewater treatment is being more and more frowned upon because of the potentially toxic elements that are present, as well as potential biological hazards associated with it. And there are a number of considerations that have to be taken into account when you're applying treated sewage sludge to land in terms of the conditions of the land and what's present in the sewage sludge. We looked at the sludge from the point of view of how much is truly beneficial being released from that, and that's what you can see in the plot on the right. That shows you the sludge and the phosphorus that's released over time. The solid line is the inorganic phosphorus, and the dashed line shows you total phosphorus. So when you apply sludge to land, you have a very quick release of organic phosphorus that can wash out of your system very quickly, and then not a lot else is coming out, which means that it doesn't last very long as a soil amendment. You have to keep applying it in order to be useful. So we've looked at smoldering as an opportunity to transform the sludge into an ash that will better regulate the release of phosphorus. And that's what you see in the second set of lines that I've highlighted. So the dark is inorganic and the dashed is total. You can see that we have a slower release over time. We don't reach a plateau with the phosphorus that's been released. We've effectively transformed it into a solubility limited problem, and therefore releasing over time, and it's more inorganic phosphorus. We've actually retained 100% of the inorganic phosphorus content and possibly transformed some of that organic phosphorus through smoldering. I think that's where I'll end. Hopefully through the 3 case studies, I've shown the power of this methodology to understand what's happening in the subsurface and interpret what could happen. In smoldering, we see changes to pH, mineralogy, and organic matter can all affect mobility. That's true in terms of our copper, where we're not just looking at it from a remediation point of view, but also resource recovery. And finally, for smoldering of biosolids, we're looking primarily at resource recovery, recovering that phosphorus in a beneficial way. LEAF has provided significant understanding into the mobility, not just of the target elements, but of all the other elements that we've been testing as well. The next step for us is to dig more into the modeling and looking at the more extreme conditions that these materials might encounter. Thank you very much. I'm happy to take questions during the discussion session.
Great, thank you, Christine. Your talk touched on so many areas that I'm interested in, so we'll need to talk later about some of this. But great if you can hang around till the final session, and we'll have our panel discussion and we'll address all the questions there.
Okay.
Great. Thanks
Great,
again.
thank you.
Our final speaker in this session is, bear with me here, is Helen McMillan. So perhaps Helen could be made a presenter. All right, you're way ahead of me. So Helen is a principal geoenvironmental scientist within RSK's Geoscience division. She is a chartered geologist and an ASOBRA, controlled waters, with over 15 years experience working in environmental consultancy, specializing in contaminated land management, and environmental compliance projects for a range of private and public sector clients. Helen's key area of expertise is in hydrogeological risk assessment and contaminant transport modelling. She is skilled in the use of CONSIM and RTM. Helen takes pride in developing robust, practical, sustainable and cost-effective solutions to environmental problems on behalf of clients. And Helen is also leading the SOBRA subgroup on controlled waters and climate change. So over to you, Helen.
Hi, good afternoon, everyone. Hopefully you can hear me. I'm going to switch my webcam off for the presentation. I'm just worried the bandwidth's going to cut out. You're not going to hear everything, but hopefully you can see my screen. Let me know if that's not the case.
Helen, you just want to make it to presenter mode? And to slideshow?
Oh, yeah. There, is that better?
Super, that's you. Thank you.
Yeah, great. Okay, so as Keith introduced me, my name is Helen McMillan and I'm a Principal Geoenvironmental Scientist at RSK. I'm also leading the SOBRA subgroup that's in the process of developing guidance, which will consider how climate change effects should be incorporated within controlled waters risk assessments. So today I'm going to provide you with an update on the current findings of the subgroup, and you are the first audience that are getting to hear about our initial thoughts, which is quite exciting, so I'd welcome your feedback. So before I go any further, and as we're part of in Scotland, I should point out that controlled waters is the terminology used in England and Wales to define all wetlands, rivers, lochs, transitional waters, coastal waters and groundwater. The equivalent term in Scotland is the water environment, and in Northern Ireland they seem to go between the two terminologies, perhaps with a slight leaning to the Scottish version. So why is the subgroup needed in the first place? So within England and Wales, the need to incorporate the effects of climate change into qualitative and quantitative risk assessments is set out within GPLC2, the National Planning Policy Framework, and LCRM. We've also got British Standard 21365, which was published last year, and this states the need to consider and identify possible foreseeable events within your conceptual site model. So these could be things that would affect contaminant impacts or create new exposure pathways, such as flooding, rising groundwater or seawater levels, and extreme weather. And these all go hand in hand with climate change. In Scotland, while climate change is considered by SEPA to be one of the biggest challenges in environmental regulation as part of delivering its One Planet Prosperity strategy, there's no further information or mention of it within any land contamination guidance document relevant to Scotland, such as WAPPS 10. Currently, the main focus of UK climate change guidance relates to surface water flooding and abstraction, and quite rightly so, given the potential consequences and impacts climate change could have if we weren't prepared for this. However, as a land contamination practitioner, I think there is a clear need for guidance to be developed to ensure climate change is considered and applied consistently across the industry, to ensure that controlled waters risk assessments we are completing are sustainable and robust. And I'm not the only one, as at the SOBRA AGM held in December last year, our members voted in favour of creating a new SOBRA subgroup focusing on controlled waters and climate change. And this is our subgroup. We formed in May 21, May this year, and there are 14 of us represented by a mixture of consultants and regulators. So I think it's particularly important to highlight that we've had regulator involvement at the outset, as after all, the guidance that we're producing has to stand up to their scrutiny and standards, and we hope that this will provide an added degree of robustness to the guidance. SEPA in particular, I would say, have been great at providing us with an initial steer as to what their aspirations for the guidance are. So our aim is to develop clear practical guidance to support decisions about the potential effects of climate change through all stages of land contamination, controlled waters, risk assessments. We envisage the guidance document will include an initial literature review comprising an overview of existing guidance and how climate change is currently affecting and likely to affect the UK in the future. We're also going to look at how the effects of climate change should be incorporated within the CSM through all stages of risk assessment, from PRA through to GQRA and DQRA. And we're also going to have signposting towards useful data sources relating to climate change. So over the next few slides, I'm going to provide you with an update on our progress in relation to these aspects. So I've already said there is an absence of guidance relating to climate change and land contamination, but how is climate change affecting the UK? So the State of the UK Climate 2020 report contains a number of statistics and trends associated with the climate in the UK, some of which you can see on this slide. So the key points to note are that the UK climate is changing. Recent decades have been warmer, wetter and sunnier than the 20th century. And the year 2020 was the 3rd warmest, 5th wettest and 8th sunniest on record in the UK. And it's the only year to feature in the top 10 for all 3 categories. Climate change is also likely to result in more intense and extreme weather and significant weather events with a higher likelihood of heat waves, flash floods and droughts. And you only have to look at the weather that we've been experiencing over the last couple of days, where yesterday there was record-breaking temperatures in Scotland, and then you get today, the heavens have opened and got a lot of rain, at least where I am anyway. So extreme weather is becoming a bit more common. So this next slide, it shows projected future climate change effects and influences across the UK from the UK Climate Projection or UKCP 18 project, and this is for the projecting into the future for the period 2061 to 2080. So UKCP 18, it basically projects there being a greater chance of hotter, drier summers and milder, wetter winters, along with an increase in the frequency and intensity of extreme weather. So the first image we've got up at this kind of top left corner shows temperature projections, with all areas of the UK projected to experience warming, with warming greater in the summer than the winter. It also shows that southern England is projected to warm more than northern regions in the UK. And then the graphics down here show precipitation projections. So in terms of precipitation, rainfall patterns across the UK aren't uniform, and they vary on seasonal and regional scales, and they will continue to vary in the future. Average rainfall is expected to increase in the winter months, but reduce in the summer months, as shown by those figures. You also have regional variations. So for example, you can see differences between southern England and northern Scotland. Then we've got this top right-hand graphic up here, which is showing kind of sea level rises, and sea levels rising due to melting polar ice and thermal expansion of the oceans. The pattern of sea level rise is not uniform across the UK, and that's mainly down to the effects of isostatic rebound from the last ice age that we had. And sea level is predicted or projected to rise less in the north and more in the south. Just something to consider and point out is that the figures that you're seeing, they show regional climate projections from the high emission scenario. This is representative concentration pathway, or RCP, 8.5 for the period 2061 to 2080. So RCP 8.5, this is the most extreme scenario, and it assumes that the world does nothing to combat greenhouse gases, with global temperatures changing by 4.3 degrees. So while RCP 8.5 may be a suitable projection for aiding in water resource planning and flood risk management, does assessing the effects of climate change on land contamination warrant such pessimistic assumptions? perhaps a more middle of the road projection such as RCP 4.5, where temperatures are projected to change by 2.4 degrees might be more suitable. Here we go. This slide is just sort of kind of recent headlines where climate change has hit the news, and it really, these are just from over summer, and it just sort of shows how we're kind of experiencing much more kind of extreme and intense rainfall, from you know, flooding through to drought fears. So. Okay, so what implications does climate change have on the conceptual site model underpinning our land contamination assessments? So this slide's just showing a typical conceptual site model. We've got a land contamination source shown by that red blob up in the top left of the slide. And we've got various pathways, both above and below ground, by which it may affect nearby controlled waters receptors. So that could be your groundwater bodies, abstraction wells, surface water bodies, so both freshwater and also kind of marine surface water, and also groundwater dependent terrestrial ecosystems. So the next few slides, I'm going to show changes that may occur to the CSM as a result of climate change. So this slide shows changes to the CSM that might result due to extreme high intensity rainfall events, and also more long-term effects as a result of increased average annual rainfall. So I'll just go through some of these that you can see in the slide. I appreciate that the rating's not very big. So in terms of surface or near surface effects, you could get increased rainfall and infiltration, resulting in increased recharge rates and runoff. You could get erosion and remobilization of the source zone down to extreme heavy rainfall. You could also get erosion and or flash flooding, causing changes to overland drainage pathways and pathway lengths. Localized surface water flooding might also occur, and this may affect pathway lengths, peak river flows, and could mobilize contaminant sources that may be upstream of your site. So some of the impacts may vary depending on whether you've got any man-made flood defence barriers in place and whether they're maintained as well. Within the subsurface, you could get groundwater levels rising, and that may impact on whether contaminant sources are above or below the water table. You could also get introduction of drains to cope with increased rainfall, and that might result in the formation of new preferential pathways. Also, if you might get increased dilution and volumetric flow rates within the subsurface. So there are just a number of ones to consider. And then on the flip side, we've got changes to the CSM as a result of extreme heat events and average air temperatures increasing. So the slide again just shows a selection of ones that we've been thinking about. You could get increased evapotranspiration and reduced infiltration, in particular potentially lower recharge in summer months. If you've got cohesive soils at the surface, they may crack. You may get desiccation cracks forming, resulting in vertical migration pathways at the surface. You could also get increased source erosion and wind-blown transport. Rivers may start drying up, so your Q95 in the river may decrease, resulting in less dilution potential, and you may also see an increased importance of groundwater-based flow to sustain river levels. And then within the subsurface, groundwater levels could fall. That could result in the creation of perched water tables, depending on what your geology is like. You might also see that there's an increased importance and reliance on groundwater abstraction to sustain water supplies. And also you may get reduced dilution and groundwater flow rates. So one of the consequences of global warming is that average air temperatures will increase, and that might also increase the temperature of the ground and shallow groundwater and surface water temperatures. So this may have an effect on contaminant physical chemical properties, such as solubility, dissolved oxygen, the volatility of contaminants, viscosity of NAPLs, microbial activity, and reaction kinetics. So the photo I've put on this slide, I think illustrates contaminant behaviour in response to extreme temperatures quite well. So probably most people in Glasgow will remember the day the roof on the Science Centre started to melt, with a pitch-like substance starting to leak from it. This is in June 2018, where temperatures soared to 32 degrees C. So it is an extreme version of what might happen in the subsurface, but I think it kind of provides a good visual indicator. Another consequence of global warming is that sea levels are projected to rise, and this might affect the tidal limit on rivers and estuaries moving upstream. It could influence hydraulic gradients in coastal groundwater. You could see an increased risk of coastal and tidal flooding. Potentially there could be more saline intrusion, and salinity might affect contaminant mobility and affect the water quality of coastal groundwater aquifers. Some of these impacts will vary locally, and it will depend on whether natural and man-made barriers are built and or maintained. So just to summarise the CSM considerations, what we've been able to show you that climate change effects may fundamentally change the pollutant linkages being considered within the CSM, in particular source contaminant behaviour, active pathways, and the proximity to and type of receptor. Changes to the CSM components as a result of climate change could be chronic, so long duration processes. For example, this could be risk to groundwater from ongoing leaching as a result of groundwater levels rising due to increased average annual rainfall, or they could be more acute rapid events, such as the erosion of the source area due to a period of intense rainfall or drought. And both acute and chronic climate change effects should be considered within the conceptual site model. Also showing that there's regional variability across the UK with respect to how climate change is being realised. So climate change effects need to be considered at a site-specific level. There isn't going to be a one-size-fits-all approach. Climate change also needs to be considered at the outset from the PRA stage. It shouldn't just be an afterthought or something that is bolted onto the sensitivity analysis within a DQRA. Okay, so what next? So we've now got a bit of a better handle on how climate change may affect and influence the CSM. So we'll next be turning our attention on how this could be assessed at the GQRA and DQRA stages. Within the DQRA, we'd originally intended to create parameter ranges for key determinants that may be influenced by climate change. However, due to the regional variability across the UK, is this still the correct approach to take? Perhaps it may be more suitable to provide risk assessors with signposting to the relevant data sources, accompanied by a couple of worked example case studies showing how you could use the data. We also need to consider what climate projections we should consider for land contamination. Do we go for a very conservative worst case approach, such as RCP 8.5? Or would something more middle of the road like RCP 4.5 be more suitable? So these are things that we're going to be discussing at our next subgroup meeting next week. Ultimately, our aim is that we will have a draft copy of the guidance to the SOBRA Executive Committee by the end of the year, with a view to having it published early next year. So watch this space. And as I said, it is an evolving guidance document. We're still in the process of going through the data. And if anyone's got any feedback that they would like to provide based on what I've presented today, then please get in touch. My email address is shown on the slide there. So just before I finish, I thought it would be useful to leave you with some useful links that you can explore to find out a bit more about climate change and its effects, particularly in the UK. Includes some of the data sources I've mentioned, such as the State of the Climate 2020 report and also UK CP18. So you'll be getting these slides emailed to you, so you don't have to rush writing them all down, but there are a few useful links there if you want to find out a bit more. So that's the end of my presentation. Thank you for listening, and yeah, if anyone has any questions, I'd be happy to answer them.
Great, thank you very much, Claire. That was a very topical talk. I wondered if we could maybe bring back our other speakers from this session. if you could put on your camera. Great. So we have had a few questions being submitted via the various forums. The first of these is a question for Claire regarding the asbestos dustiness method. And the question is, has I2 compared data from the lab test versus field data?
Yeah, we have actually. We've had a few projects where the client's been using pop-up tents on site, and they've submitted samples to us for laboratory testing. They've obviously looked at their fibre count data, we've generated ours, and actually it provides really good correlation, almost like a one-to-one line fit of the two comparators. So actually it does seem to be a good model for replicating that test method, which is really good. Not published in the wider domain yet, but you know, it's on its way.
Great. And a second question from Claire. You're obviously gathering a lot of real-world data. Is anyone pulling together the results to see if there are any commonalities, for example, guidance on effective suppression or different soil types, weather conditions, etc.?
Well, actually, it's interesting you say that, because we're involved in a few industry-wide projects with sort of some very large large property owners in the country, for want of a better way to put it, where we have been looking at exactly that, looking at how different soil types behave as well. That, I believe it's on its way to be published later on this year or early next year, along with all the relevant field data to match it up. So yeah, there's more data to come. We obviously sit on loads, but we don't always have all the field information. So this is quite useful because it provides the two together, which obviously gives the contaminated land sector more information to then make informed decisions on.
Great. And one question I had was whether you were using any electron microscope techniques for fibre identification or? Not
yet. I think it's going to be one of those chicken and egg situations. All of a sudden we're going to need to, and it's in the case of, oh, we need to get that now and sort it out. There used to be a very expensive investment in a piece of kit and difficult to necessarily justify without the workload. That is starting to change. So I think we stand a good chance of that becoming sort of part of a standard method, but not at the moment. We have other avenues we can go to if we do need to get it done, but not in-house.
Right, great. And a question for Christine. Let's see, how do you view smouldering combustion in terms of sustainability?
That's a really interesting question, because with everything, there are trade-offs. I remember the first ever conference I went to, somebody was complaining that, well, you're making carbon dioxide, so your process can't be good. But when you compare to other types of remediation, it depends how long you're going to take, and sampling, monitoring, other equipment that's out there. It actually lines up from a carbon point of view quite favorably, and certainly much more favorably than things like dig and dump. So even though we are generating carbon dioxide, it's a very fast process and it's a very efficient one, because we're not leaving anything behind after the remediation.
Right. Great. And one question I had, Christine, was I know there are methodologies for determining the acid rock drainage budget of tailings and any leachate from that. I wondered how those compared to the kind of leaf methods.
I'm not familiar with the acid tailings type testing, so I don't know that I can comment specifically on those. The advantage that you have with leaf is that you can vary the conditions significantly, because you have, so your leaching itself, you're looking at native conditions and how that changes over a very short period of time. So if you start off with a pH of about 5 in your material, it might increase a little bit or decrease a little bit based on the water that you're putting into the column. However, couple that with method 1313, you can look at what happens when your availability, when your pH changes. So if you're around about neutral conditions, you're usually at the lowest point in the solubility curve. But if you shift into more alkaline, or sorry, more acidic conditions, like with the copper mine tailings, then that availability is going to change significantly, and the copper is going to come out of solution. So by pairing the two together, you can view that, and you can also there are a couple of metrics for determining availability limited versus solubility limited. So you can get an idea of how much more might come out beyond that 10:1 liquid to solid ratio.
Mm-hmm.
So there's a lot of power there, but there's a fair amount of witchcraft also that goes into interpreting it.
Right. Okay. Great. Moving on, a question for Helen. How do you understand the risk-based decision making in contaminated soil or land you mentioned? Does that make sense? I don't know.
What was the question?
Oh, okay. How do you understand the risk-based decision making in contaminated soil or the sites that you mentioned?
In terms of climate change, so I'm not sure I fully understand the question.
Yeah,
because
just a clarification on that. The risk-based decision making in one of your slides. How is it justified? How do you understand that in terms of contaminated land?
Sorry, I'm not sure what slide was.
Yeah, sorry, maybe I could ask the question asker to maybe rephrase that question. And in the meantime, I had a question of my own I wanted to ask, and you know, some of the experience that I've had, you know, has been contaminated land that's been really impacted by accelerated coastal erosion. You know, where you've got you know, landfills being exposed that were, you know, maybe 50 meters away from the shoreline. Does anyone have a good, you know, handle at how many potential sites in the UK might be, you know, at risk from erosion? And I'm assuming these are kind of sites that have been previously remediated, perhaps by capping, that could be at risk for coastal erosion.
That's a good question. I'm not sure if anyone does have a full record of it. Obviously, if it's something remediated under Part 2A, local authorities will have that recorded. Where it's been voluntary remediation under planning, maybe less so in terms of having something fully documented there. But I think this is part of the reason for this guidance. It is really to make sure you are considering future potential climate change effects, so that for example, if you have got a coastal site, that you are kind of thinking, well, could there be erosion up to my site boundary? Could this site, you know, be eroded away? And it's those factors that we're really wanting to kind of capture and make sure they're considered within the risk assessment process. So it might be okay now, but I don't know, 30 years down the line, could it then be landing in the North Sea? So those are really things, and that will really inform the decision making as to what sort of degree of remediation you need to do, if you're doing a DQRA and looking at kind of migration of contaminants down pathways, what pathway length is more suitable if it's potentially going to direct discharge into the sea by erosion processes. So that really is something we're kind of hoping to consider in the guidance. As I said, coastal erosion is going to be different in different parts of the UK. And a lot of it's linked into the sort of kind of land rise and fall. So in England or southern England, you've potentially got more effect of that than up in northern Scotland, but it does vary locally as well. That's why there's not really a one-size-fits-all approach. It really does have to be looked at a site-specific kind of level. And if you have got a site near the coast, then those are things that you really need to kind of have an understanding on and a good grasp of.
Right. Okay. And just a bit of clarification from Dave Cook, who believes there is a working group looking at coastal landfills, but he doesn't think they go into the types of contamination at these sites. Great. Question for Helen. Should operators be expected to redo their risk assessments given the significant changes in risk due to climate change?
I'm not sure that's a question I should be. That's not really a question for me to answer. Really, what we're doing as a subgroup, I'm a consultant by trade, and we are just wanting to make sure anything going forward is considered robustly. Things that have happened in the past, been approved. That's not anything that I have control of. I'm not a regulator. I guess that's up for regulators to have a think of. And if there are risky sites, I suppose, that might be getting flagged due to these extreme weather events and climate change, that would be something to be looked at. But that's not the focus of our subgroup. We're kind of really wanting to make sure going forward we are looking at these at all sites and having climate change in mind and how that may affect our conceptual site model. I should also say maybe it's for sites where risks are clear cut, it's not an issue or there is a significant issue. It may not be, it may not change anything that much. It may be your more borderline sites where it's just falling under your remedial target or it's just over. It's those sites that it may have, may actually say, well, actually, if you were to consider climate change, we say there's no risk, but it's like, I don't know, just at or below the remedial target you're looking to, or your assessment limit you're looking to achieve. Maybe then you maybe need to consider doing a bit of remediation to make sure if any, for example, groundwater levels rise and you're, whereas you may have had an unsaturated source zone beneath your source. If that was to go, then that could kind of really affect your risk assessment. So it's sort of trying to think about it in those terms as well.
Great. Okay, and I think Dave Cook has posted a link to some reports there, which I think will be available to all the attendees. Alison?
I'll copy it into the chat.
Great. Okay, well, that's probably a good point to conclude this final session. I'd like to thank all our speakers once again. Very great topical presentations, and thanks again. Alison, did you want to kind of jump in to kind of round things up?
Yeah, Eve's going to do the thank yous and goodbyes.
Yeah, so just really wanted to say thank you to everyone who's made the conference such a success. All of our chairs, presenters, all of the backstage staff behind the scenes, everyone has been working hard to make this happen, and a huge thanks to all of our supporters for both days of the conference and allowing us to get the webinar software that we ran the conference with, and allowing us to keep the ticket price so reasonable. I hope everyone has enjoyed it, got something out of it, and yeah, really appreciate everyone who came along and joined in. I think it's been a good success. So yeah, I will wrap that up and say goodbye to you all now, and yeah, thanks very much to everyone who's made it what it has been.